An RC circuit is a circuit that contains both a resistor and a capacitor. Now let's imagine that this resistor and capacitor are hooked up to a battery and that there is a switch that is open that keeps current from flowing in this circuit. Initially, the capacitor is uncharged. When we throw the switch, the battery will start pushing current around the circuit and the capacitor will start to charge. So if we look at a graph of charge on the capacitor versus time, we can see that that charge will be increasing. But the rate of charge is slowing because as the capacitor charges, it becomes more and more difficult to add additional charge to the capacitor. So tau is a time constant for the circuit. Tau is equal to the resistance times the capacitance, and if it's large, it takes a long time to charge up the capacitor. So tau tells us how much time it takes to charge up the capacitor to roughly 2/3 of its final value. Eventually, the capacitor will come to its final charge, and the charge would be equal to the capacitance times the voltage of the battery. Now, this is just the capacitance equation, C equals Q over delta V, that's been rearranged. So you'll always build up to the same final charge of the capacitor, and the charge that you build up to depends only on the capacitance and the voltage of the battery. The function of the resistor in this circuit is to control how fast that capacitor charges. So we can write a charging equation which describes how much charge is on the capacitor after you flip the switch as a function of time. And you can see that the final charge, or the charge at any instant of time, is equal to the final charge, that maximum charge, times 1 minus e to the minus t over RC. And you can rewrite RC as tau. The current is going to be decreasing as the capacitor increases its charge. As the capacitor gets more and more charged, the current will slow and slow as it becomes harder to deposit charge on the capacitor, and finally it will die away altogether. So the current in the circuit is equal to Ohm's law, the voltage over the resistance, but then we multiply that by this factor that describes how the current is dying away. And it also depends on the time constant for the circuit. Now, if we take out the battery with the capacitor being charged and have a open switch so that no current can flow, take the battery out and then close the switch, the capacitor will discharge. The capacitor will act as a source of voltage that pushes charge around the circuit until the capacitor discharges. So at any time, the voltage drop across the capacitor is equal to its charge divided by its capacitance. And the charge on the capacitor will decrease with time, and tau now becomes the amount of time it takes to discharge 2/3 of the charge of the capacitor. So we can describe the amount of charge on the capacitor as it's discharging as being equal to the maximum charge that it started out with times e to the minus t over RC. So let's next consider this example problem. We have a voltage source of 10 volts connected to a series RC circuit where we have a resistor with a certain value and a capacitance of 3 microfarads. Find the amount of time required for the current to decay to 5% of its original value. So we want to know what's happening with the current. How long does it take the current to decay away until it's only 5% of what it started with? So let's first just draw a picture of this circuit. So in this circuit, we have a voltage source that's 10 volts. We also have a resistor, and the resistor has a value of 2 times 10 to the 6 ohms. And we also have a capacitor in the circuit, and the capacitor has a value of 3 microfarads, 3 times 10 to the minus 6 farads. Now all of these are presumably connected with a switch, and when the switch is closed, the capacitor starts charging up. So when the switch first closes, we have an amount of current that can be found using Ohm's law. And then that current dies away. So the current at any later time, so this is instantaneous current since I'm using a lowercase I, is equal to the voltage of the battery divided by the resistance of the resistor. So this is just Ohm's law rearranged. Voltage equals current times resistance. And this gives us the value of the maximum current in the circuit. So when the switch first closes and the capacitor isn't yet charged and it doesn't start resisting the accumulation of charge, then this current just follows Ohm's law. But then since the capacitor is there and it starts charging up, this current dies away. So we need to multiply the voltage over the resistance by e to the minus time over RC. So the thing we're told in this problem is that we want to find the amount of time, so we want to find t, the amount of time for the current to decay to 5% of its original value. So I max is the original value, that's the starting point, and we want to know when is I equal to 5% or 0.05 of I max. So I can rewrite this expression as being equal to, let's see, first off I have I on this side, which I know is 0.05 times I max is equal to voltage of the battery over resistance of the resistor, that is I max, times e to the minus t over RC. All right, so my I maxes will cancel. I have one on either side, so I can divide both sides by I max and get rid of that. So now I have 0.05 is equal to e to the minus t over RC. And I want to solve for t. So to undo the e to the, I need to take the natural log of both sides. So natural log of 0.05 is equal to, the natural log undoes the e to the, so over here I get a minus t over RC. So then I just need to multiply both sides of this expression by negative RC. So t is equal to negative RC natural log of 0.05. So then let's plug in some numbers. The resistance of the resistor is 2 times 10 to the 6 ohms. The capacitance of the capacitor is 3 times 10 to the minus 6 farads. And then I have the natural log of 0.05. So that's going to give me a value of positive, because the natural log of a number that is that's less than 1 is going to be negative. So I end up getting a positive time of about 18.0 seconds. So it will take 18 seconds for the current in this circuit to die away to be 5% of its original value.